Okay, so I'm going to make another function here. It's going to be a little bit different, where instead of having just a single function I'm going to rotate around the axis, I'm actually going to have two different functions. And what's that going to do for me? Well, I'm going to have y equals x, and I'm going to have y equals x squared. Now what does y equal x squared look like? Well, it's a parabola. But I'm going to look at this, and I'm only going to be interested in this part right here. And I'm going to say that part right there, so I'm going to ignore everything else. Say we've got these two functions, y equals x squared and y equals x, and I'm going to rotate those around the x-axis. But when I do that, what's going to happen? Well, I'm going to get a mirror image of this, which is going to look a lot like this. Okay. So that is not a solid like we're accustomed to. That has a hole in the middle of it, right? Right here, there's going to be a hole in the middle of it. Here, there's going to be an itty-bitty hole. But still, the same process. What's it going to do? It's going to form like a bowl. It's connected down here at the bottom. And then, you know, as you look down, it's going to be opened up like this, if you were to rotate this over this way. So it's going to kind of look like a bowl that's on its side, like that. So as I rotate that, again, I'm rotating around the x-axis. Therefore, I'm going to look at a slice that looks like this and say, well, what does that look like? Well, it's, as was the last case, it's going to form a circle that has a hole in the middle of it. What do I do with that? Well, I need to know what those radii are. Now in the other case, the last case that I did, one of the radii was just 1. That was easy. But this one, the inner radius, that's changing. It's not consistent. The outer radius is also not changing, so I need to be more careful with this. So I got some little radius r, got some big radius, big R. And what do I know about these? Well, this inner radius, what is that? That's up, that's from the or the x-axis up in the y direction. So that's the y on the inside, okay? And big R is in the y direction up to the outside. That's the y on the outside. But then I look at these and I say, well, what y is this? Well, I've got two y's given by curves right here. And the R inside is given by the curve y equals x squared, right? That's the curved piece of this. So this must be y inside is right here, and y outside is this one. So y inside is x squared, and y outside is just x. And of course my limits here, where do these things intersect? 0 and 1. So that's the domain that I'm looking at to find this thing. So now I look at this and I say, okay, so area of the big circle is what? Pi times r squared, which is x squared. Area of the little circle, little r, pi times little r squared, x squared squared, x to the 4th. My integral in the x direction, I'm going to add up everything from 0 to 1, right? And so I end up with this integral from 0 to 1. These various slices that I add up are all going to be in the x direction, so it's a dx. And my big circle is pi big R squared, which is pi x squared, minus pi x to the 4, which is the little circle. It's on the inside. Both of them are moving targets here. Last time this was just 1. This isn't 1 here. But still, simple integrals. Pi x cubed over 3 minus pi x to the 5th over 5. Evaluated at 1, 0. I plug in 0 here, I'm going to get nothing. So this is going to just give me pi over 3 minus pi over 5, which is 5 pi over 15 minus 3 pi over 15, also known as 2 pi over 15. And that's the area of this surface that would, this volume that would be formed by rotating that around the x-axis. Now, interestingly, I could take exactly this same function, or the same set of functions, and I could say, no, I don't want to rotate that around the x-axis. I want to rotate it over here. Now it's going to form a different shape. Right over here, the curve was on the inside. Over here, the curve is going to be on the outside. And again, it's going to look roughly like a bowl, but I have to redo this if I'm going to do that. Same functions right there, but I'm going to erase everything else. And we'll say, okay, I want the volume that's formed by rotating this thing this way. Well, now what do I have? Again, if I take a cross section this way, slice and look at it, it's still going to look like that. It's got some R outside. It's got some r inside. But having taken a slice this way, I know that my integral is going to be dy. So I have to be careful, make sure everything's in terms of y. Now, the inside goes from the y-axis out to the straight line. My inner curve here is the line, it's this one. So r inside is y inside, so I just flip-flop these two because they're reversed roles, y inside, which is in this case just x. That's the inside one. The big circle, the one that comes out to here, comes out to the curve. So r0, which is the outer radius here, which is x squared, except I can't put x squared. I want to put things in terms of y here. So when I look at this, I say, well, y0 is x squared. That means x is square root of y. And again, plus or minus square root of y technically, but where we're looking, it's just square root of y. And so that tells me that that is square root of y, square root of x, square root of y. I said it right the first time. Okay, so when I say pi r squared, what do I have? I have pi times y. And when I say pi little r squared, I have pi, and again in terms of y squared. So my function ends up, my area is pi y minus pi y squared, and I need to integrate. Now where do I need to integrate? I need to integrate wherever these things are in the y direction. Starts at 0. How far does it go? Well, right here in this particular function, not only is x from 0 to 1, but if you look at what y is when x is 1, y is 1, so the integral still turns out to be 0 to 1. Not necessarily going to be that way. If we went from 0 to 2 here instead, then x would go to 2, but y would go to 4. So we have to be careful of that. But now, again, the integral itself is an easy integral. Into which I need to plug 1 and 0. I get pi over 2 minus pi over 3, which is 3 pi over 6 minus 2 pi over 6, which is pi over 6. And notice that not only did rotating it this way change what the shape was, it also changed what the volume is of whatever it is we're getting. The other way, my area was different than that. Right here I've got an integral just gives me the volume of pi over 6.